All right, so we're going to be taking a look at homework for chapter 3.7. So I'm just going to start right now. Here, chapter 3.7. Homework. Let's see if I can do it like this. Okay. Good. Okay, I'm trying to look on the screen and look on my tabletop at the same time. Okay, so chapter 3.7. So 3.7, we're talking about, we're looking at calculate the mass of the solid. Mass of the solid. Okay, this is question number 7 is the first one that we're going to be doing. So mass of the solid, and this is going to be a massive revolution, right? So we're going to solid a revolution. We're going to rotate it around some axis, and then we're given some density function delta, and then well, let's see, it's going to be as a function of the radius. Okay, so on this one, we're given our delta radius. Our density function is r plus 1. And then we're given the curve y equals radical x. Okay, and we're going to go on the interval 0 to 4. We're going to go about the y axis. Okay, so let's take a look. So the first thing we're going to do when we do this is I'm just going to sketch it out so I can visualize. So this is from 0 to 4. Okay, so this is 1, 2, 3, 4. And I'm going to just kind of map out a mirror image on the other side. So now radical x means, right, when x is equal to 0, y is equal to 0. When x is equal to 4, y is equal to 2. And it's kind of this curvy line like this. This is y equals radical x. And then over here, sort of a mirror image like this. Okay, so this is our solid right here. And then they want us to go around the y-axis right here. Okay, so what we're going to be doing is I'm going to rotate like this, and it's going to give me a circle like this, sort of this shape that goes around like this around our y-axis. Okay, so now what I'm going to do is I'm going to be thinking about this. Okay, my delta r from here. So let's see, how do I want to set this up? So if this is y equals radical x, that means that if I square both pieces, I'm going to get x is equal to y squared. Okay. Now my volume, right, is going to be 2 pi x times the height as a function of x. And then dx is the thickness of each. This is our shell method as we're going around the y-axis. Okay. And remember, our mass, dm, is equal to our density function, so function of x, times dv. Okay. So I'm going to integrate this, I'm going to integrate this, and this is going to give me the mass. So I'm going to go from x equals 0 to x equals 4, right? This is, I'm going to convert this to x plus 1, because that's my x distance, right, from my axis of revolution. This is my y-axis here. This was just kind of thinking about, like, did I need to convert this or not? It looks like I don't need to do that. Okay, so now I'm going to multiply this by my shell method, which is going to be 2 times pi times x to the 1/2. This is my y equals radical x right here. Okay, and then this is dx. All right, so now when I want to multiply x times x to the 1/2, they have the same base. So this is like x to the 1 plus 1/2, which is x to the 3/2. Okay, so that's what it's going to look like here. So this is going from 0 to 4, x plus 1 times 2 pi x to the 3/2 dx. Okay, so now what I'm going to do is I'm going to distribute this x plus 1 with the 2 times pi x to the 3/2. Actually, first I'm going to factor out the 2 times pi out of my integral because it's just a constant term. Okay, so I'm going to go x times x to the 3/2 gives me x to the 5/2 plus 1 times x to the 3/2 is just x to the 3/2, oops, 2 times dx. And this is going to give me 2 pi from 0 to 4 x to the 5/2 dx plus 2 pi from 0 to 4 x to the 3/2 dx. So what I'm going to do is the power rule on this one right here. Okay, so this is going to give me 2 pi times x to the 7/2 all over 7/2, right? So I'm integrating x to the 5/2 plus 2 pi times x to the 5/2 all over 5/2, right? Because I'm integrating x to the 3/2, and I'm going to evaluate this whole thing from 0 to 4. Okay. Now I'm going to get 2 pi. I'll factor out the 2 pi. So I'm going to get 2 sevenths, right? So that's because I divided by a fraction, times 4 to the 7, oops, 7 halves, plus 2 fifths, right? Because I divided by a fraction, 4 to the 5 halves, okay? That would be minus 0. All of these terms have a 0, so I'm not going to worry about that. Just put minus 0 here. Which is equal to 2 pi times 2 sevenths times 128 plus 2 fifths times 32, which is equal to 2 pi times 256 over 7 plus 64 over 5. I need to find a common denominator and multiply through. My common denominator is 35. Since if you want to keep things in fractional form, you can just multiply it through if you want to, but 448 over 35, which is going to give me 3,456 times pi all over 35. And that gives me my mass of this solid of revolution as I go around the y-axis. Okay? Okay, so that's question 3.7, number 7. How you doing? Okay, so now the next question that we're going to take a look at is question 15. Okay, question 15, let me just read the question itself. Question 15 says, we're given the length density function, which is our delta L. Okay, could be, so it can be in terms of x. And this is going to be about a wire. So basically, we're dealing with this like almost like a two-dimensional, or like you can kind of think about it as like a one-dimensional shape. Okay, lying on the x-axis over a given interval. For each problem, calculate A, the total mass of the wire, and B, the mass midpoint. Okay, so I kind of did an example like this that was up on YouTube, but I'll just work it through again. Right, so question 15 says, we're given our delta length function is x plus 7, and we're going to go from 0 to 4 in terms of our x value. Okay, so let's see. I hope you guys can see that. Okay. All right. So now we're given this here. So what I need to do, so part A, I need to be able to calculate the mass. Okay. So the mass is simply on this two-dimensional shape. I'm going to go from my x equals 0 to my x equals 4, and I'm going to integrate my length density as a function of dx, right? Because it's just this tiny little thin wire. And then I'm going to go, you can kind of think about it as a wire that goes from 0 to 4, 1, 2, 3, right? And it has this like density across it. Okay, so my density, it's not a constant density. It's like maybe here it's a little heavier than here. I mean, you just never quite know. Okay, so as we go across, this dx says I'm doing this infinitesimally thin little slice of the wire. And what's my density at that particular point right here? It looks like our density is increasing linearly as we go from 0 to 4. Okay, so this is just a simple integration with our power rule, right? So this becomes 1/2 x squared plus 7 times x, and I'm going to evaluate it from 0 to 4. Okay, so I'm going to plug in our values here. I'm going to get 4 squared over 2 plus 7 times 4. And if I plug in, this is 0 and 0, so I just subtract out 0. So this is going to be 8 plus 28 equals 36, and I think our units maybe were in kilograms. Okay, so that's 15A, which is just the mass of our wire from 0 to 4. Okay, now the mass midpoint, okay, it requires a lot of algebra, but it's basically like saying, I can't just go, okay, I'm just going to cut it in half, so 0 to 2 and then 2 to 4. I don't know actually where the mass midpoint is going to be, because remember, this says our density is increasing, right, as I go from 0 onwards, and my density is increasing linearly. So my midpoint is going to be somewhere, who knows where. So I need to be able to calculate exactly where that's going to be. So what I'm going to assume is, right, my midpoint, I'm just going to pick a spot. I don't know where it is. I'll call this xm is my midpoint position. Okay, and what that means is that the mass here is equal to the mass there. So the mass from 0 to x of m is equal to the mass from x of m to 4. So what that means is I can go on my integral, there. I can go my integral from 0 to x of m, right? And I'm going to integrate my x plus 7 dx, right? So this is my delta length density here, right? dx, and that's going to equal to x of m to 4. And I'm going to integrate x plus 7 dx, right? So I took this delta length density, right? And I said the mass from 0 to x is equal to the mass from x to 4. Okay, so again, we're going to be integrating on both sides. So what this is going to look like is 1/2 x squared plus 7x from 0 to x of m equals 1/2 x squared plus 7x from x of m to 4. Now don't be fooled and think, oh, I've got this x squared on both sides, I'm just going to cancel things out. Because watch, our fundamental theorem of calculus says, right, I have to do my f of b minus f of a, and I've got these values here. So I'm going to start working through the algebra on doing these pieces here. So dealing with this side of the equation first, I'm going to go 1/2 x of m squared, right, because I'm plugging in x of m everywhere I see an x, plus 7 x of m. Now I would subtract out 0, but I don't have to worry about it because it would just be 0. Equals, let's do it on this side here, right? So this is going to be 1/2 4 squared, okay, plus 7 times 4. Okay, so that's what we did over here. So it's going to be 36 minus, and I'm going to plug in x of m into everywhere that I see here. So this is x of m squared minus 7 x of m, right? So this is, right, I would have parentheses here, but I distributed, right, because this is my fundamental theorem of calculus, my f of b minus my f of a, and I distributed my negative to both of these terms here, okay? So now what I want to be able to do is I'm going to bring everything over to one side of the equation so I can start combining like terms, right? So I'm going to add x squared of m, I'm going to add 7 x of m, add 7 x of m, add x squared of m, and then I'm going to subtract 36 from both sides. So now I'm going to get a quadratic. It's going to look like x squared of m plus, I'm sorry, this one should have been, I think, divided by 2. My bad. Okay, so this one is x of m plus 14 x of m minus 36 equals 0. So it's a quadratic, right? So what I'm going to do is I'm going to use the quadratic formula to be able to solve that. So my quadratic formula says, right, minus b plus or minus square root b squared minus 4ac all over 2a. So I'm just going to plug in my coefficients for a, b, and c. Okay, and let's do that here. Oops, I'm running out of space. So I'm going to get minus 14 plus or minus 14 squared minus 4 times 1 times minus 36 rooted all over 2. Basically, when I work through all the different algebra on here, right, I'm going to get x of m is equal to 2.21. And I want the positive aspect. If I get two solutions, one's negative, one's positive, I'm going to be taking the negative, right? Because this one is my positive. The other solution that we get, by the way, is x of m is equal to minus 16.2, but that doesn't make sense for what we're trying to do because our interval goes from 0 to 4. So our midpoint of mass happens when x is equal to 2.2. So like roughly right about there is our midpoint of mass. Okay, so that's question 15 from chapter 3.7. Tends to be a lot of algebra on these types of questions here, but it's not too bad, right? Okay, so our next question, 18. So I'm looking at the screen, making sure that you guys can see. Let me read the problem. So question 18, okay, so again, we're dealing with the length density. So here we have delta L sub x equals x ln of x, and we're going to go in an interval 3 to 9. That's what we're trying to do here. Okay, and I think this one, if I look at it from our book, it's got a little, one of those little triangles with a circle in it. That means that your book actually has like a solution for it. So if you go into your textbook and you click on this button here, you can't do it on the homework that I've given to you because it's just an image, but if you click on this button here from your textbook, then it'll open up a YouTube video for you of somebody actually working it through, so you can take a look. Okay, so the first thing that we want to do is calculate the mass. Okay, so when we go to calculate the mass, right, so we're going to be integrating from 3 to 9. We were given that interval here. We're going to go x ln of x dx. Okay, so for this one, I need to do integration by parts. This is a good review on how do we do integration by parts. Okay, so the way I set it up, remember when we do integration by parts, right, I need to be thinking about what's going to make stuff easier. So if I choose u as the ln of x, right, and I take my derivative, right, the derivative of our natural log is 1 over x. If I take my dv equals x dx, and I integrate both pieces, I'm going to get v equals 1/2 x squared. Okay, so remember our formula for integration by parts, right, is going to be uv minus the integral of v du. Okay, so I'm just going to plug in those pieces, and I'll do it over here. So I'm going to go uv, so ln of x is our u, times v, 1/2 x squared, minus the integral of v, 1/2 x squared, times du, which is 1 over, this should be 1 over x dx, right? So now I'm going to get, this is x squared all over x times 1 over 2 dx, right? So the x and the x squared are going to cancel each other, not really cancel, but simplify each other out. Okay, so then basically what I'm looking at when I go to integrate this, actually after I integrate it, I'm going to get 1/2 x squared ln of x minus 1/4 x squared, right? Because 1/4 x squared. So what this simplifies out to be is 1/2 the integral of x dx. When I go to integrate this, I'm going to get 1/2 times, now my power rule says x squared over 2. So 1/2 times 1/2 gives me 1/4 x squared. Okay, and I'm integrating that from 3 to 9. Okay, so when I plug in all of my pieces, right, I'm going to plug in a 1/2 9 squared ln of 9 minus 1/4 9 squared, and then minus out 1/2 3 squared ln of 3 minus 1/4 3 squared. Okay, when I actually work it out, I'm going to get my mass is 66.03 kilograms. Okay, so there was some algebra involved in here. Okay, now part B again, they want us to actually work through the midpoint of mass again. So we're going to do the same thing that we did in the previous question, okay, which means I'm going to integrate on both sides and I'm going to set things up to be equal to each other. Okay, I'm not going to worry, let's just set up, I'll do this part here and then we'll take that piece. Okay, so we don't actually have to work through the whole integration by parts again. So what this means is I'm going to break this up into two pieces. So I'm going to go 3 to my midpoint, x ln of x dx is going to equal to my midpoint to the end of my wire, x ln of x dx. Okay, so we already figured out what the antiderivative is. So I'm just going to take this antiderivative and put it into each spot. All right, so doing that, what I'm going to get is 1/2 x squared ln of x minus, oops, I keep breaking my pencil, 1/4 x squared, and this is going to go from 3 to x of m, and that's equal to the same thing, same antiderivative, ln of x minus 1/4 x squared, and now here I'm going to go from my midpoint to the end of my wire. Right? Remember, we've got this wire going from 3 to 9, and I'm looking somewhere along here is my midpoint, right? And then the density of this wire is going to vary as a function of x times the natural log of x. Okay, so as I go along this wire, the density gets bigger, because this is an increasing function. It's just sort of to visualize in my mind. All right, so now there's a lot of math involved. Okay, so bear with me. We'll just work through some of the algebra at this point right here to try to figure out what our x of m is. Okay, so I'm just going to start plugging things in. This is 1/2 x of m squared ln of x of m minus 1/4 x of m squared. Okay, minus, I'm going to plug in the 3. So this is going to be, right, if I plug in 3 squared, I'm going to get 9 halves ln of 3 minus, right, this is 9 over 4, 9 over 4, and that's equal to, right, I'm going to do the same thing on this side right here. Okay, so that's going to equal to 1/2, so let's do this, 81 times the natural log of 9 minus 1/4, 81 minus, we're going to plug in, so this is going to be 1/2 x of m squared ln of x of m minus 1/4 x of m squared. Okay, so I just did the fundamental theorem of calculus here. Okay, by plugging in my 9, and then by subtracting out when I plug in my x of m, I kind of ran out of space on here. Okay, alrighty, so here we go on our algebra. All right, so this bit here, actually I put this out on my calculator. I got this was equal to 2.69, okay, right in this piece here. So now I'm doing a little bit offline here, but now I'm going to get, let's see if I start, this is going to look like minus x of m squared over 2 ln of x of m. This is going to be plus 1/4 x of m squared, right? Because this is minus times minus, okay? So now I'm going to start maybe multiplying through these numbers here. I think when I did this offline, I got 68.73 as a number. So this was just a number, this was just a number, right? That came from plugging in 3 and plugging in 9. Okay, so now when I start to kind of try to bring things together, I'm going to get x of m squared ln of x of m minus 1/2 x of m squared equals 71.43, right? So I'm going to basically add, this was a negative, so I'm going to add both of this to both sides, and I got 71.43. Okay, so basically now what I'm going to do is I'm going to factor out, right, the x of m squared. So I get x of m squared, natural log of x of m minus 1/2 equals 71.43. And I think that there was a bunch of math involved in here, but basically, essentially what I did was I looked at, let's see, how did I do this? Yeah, I factored this out, and then I divided by x of m squared. So then I have ln of x of m minus 1/2 equals 71.43 all over x of m squared. And then I graphed it. They said we could use technology. So I did a graph of here, and I did a graph of here. I'm not showing it. Let's see, maybe I can actually do it so you can see. If you can see this here. So if I go here, so I'll graph this out. So I'm going to go natural log of x minus 0.5. I don't want it. Natural log of x minus 0.5. I have to be careful about my order operations. And then this is going to be 71.43 divided by x squared. Okay, so now I'm going to graph this out. I'm going to take a look. There's my natural log graph. And I think I'm off the screen, so let's do this. I'll set this to be minus 10. I'll just try this out first. If this doesn't work, then I'll do a zoom and see. Okay. There's my natural log graph, and there's my other one, my rational function. And it looks like they're intersecting here. Okay, so I can actually zoom in my window, so I don't really need, I'll go from 0 to there. So we'll just redraw it so we can focus in a little bit more. There's the natural log. Here's our 71.43 over x right here. So that's where we want to be able to find it. So I can look at this part right here. I can look for intersection, right? And it says my first curve is this one, my second curve is that one. And my guess, I'll just give it the right ballpark. So it tells me, right, the intersection point, 7.02. Okay. So I use my graphing calculator. I don't know if you guys can see that okay on the screen. I use my graphing calculator to help me figure out where those things are going to be, because algebraically it's a little bit too complex to do that. So this gives me the midpoint of mass for this wire. Remember, this was a wire going from 3 to 9, and I wanted to be able to find the mass of the wire, and then I wanted to be able to find the midpoint of the mass. Okay, so that's what we're looking at right here. Okay, so that was question 18. All right, question 25. Let me bring up the question so we can read it. Okay, so we're given a region B in the xy plane, occupied by a thin metal plate and an area density function for the plate. Okay, so now here we're dealing with area density function. So in the previous couple of questions, we were dealing with a wire, right? That was basically like a one-dimensional piece. It was going from, x equals one value to x equals another. And now we're dealing with a two-dimensional plate. This is considered like a laminar surface, right? So we're looking at the area density of that, because it's going to be shaded as we go, and then the area density of that's going to be changing as we go across in terms of x or y, depending on how our area density is given. So we're given area density as a function of x, or area density function as a function of y. And so we want to be able to calculate the mass of the metal plate. Okay, so question 25 says we've got the area density function. This is a function of x squared plus 1. Okay, and then our line, let B be the triangular region bounded by the axes, and the line y equals 2x minus 6. Okay, so the first thing I want to do is I'm going to graph it out just so I can visualize what's happening here. There's my x-axis, there's my y-axis. So this is 2x minus 6. So my y-intercept, 4, 5, 6, is at minus 6. right? And my x-intercept is at 3. This is just a straight line, right? But it's an increasing function. And we're bounded by the axes. So this is our thin laminar plate right here. Because the first thing we need to think about first off is this is in, right, this is our fourth quadrant. So both, so y is going to be negative. So when we actually get a value, we get an area, whatever the area is, we're going to take the absolute value of it for the mass, because the mass is essentially a scalar quantity. It's a magnitude, and so we want that to be positive. All right, so our area density, okay, is a function of x. Okay, since that's a function of x and my function that I'm given is a function of x as well, then basically I don't have to do any kind of conversion on here. It's already in terms of what I want it to be. I'm going to let my area density decide, right, whether I do this as a function of x or as a function of y. So if they had given this to me, my area density as a function of y, I'd be looking at integrating with respect to dy, okay, which means I'd have to convert this into x equals some function of y. Okay, but they gave this to me as a function of x, so I'm just going to use what I have here. So this is a function of x, so I'm going to be looking at values. I'm going to go from x equals 0 to x equals 3, so that's going to tell me, right, my mass is going to be, I'm going to integrate from x equals 0 to x equals 3, and I'm going to integrate my area as a function of x, and then I need to find out, we'll call this area of x dx. I need the area of this region right here, okay? And this is, they gave me the density function for it, so I'm just going to start plugging things in. So I'm integrating from 0 to 3. My area density is x squared plus 1. The area that I'm doing, right, is between my function and the x-axis, so that's 2x minus 6, okay, times dx. If it was between like two different functions, I'd have to subtract the functions out and do some more work on it, but it's just between the x-axis and the function itself. Okay, so for here, I need to FOIL these out to actually get like a full function, essentially a full, I can just do the power on it. So when I do first, I get 2x cubed minus 6x squared plus 2x minus 6 dx. So I can just do the power rule when I go to integrate it, which is going to give me 2 over 4x to the fourth minus 2x cubed plus x squared minus 6x. And I'm going to integrate from 0 to 3. Right, so this is going to give me 1/2 3 to the fourth minus 2, 3 cubed plus 3 squared minus 6 times 3. And I'm going to take the absolute value of that, because that's what happens. I get 22.5, but my mass needs to be positive because it's a magnitude. So I get a mass of 22.5 kilograms. And I think, did they give me the units? Let's see. I don't know if they gave me the units or not, but I'm just going to assume it's in kilogram units. Okay, so that's 25. Okay, so let's take a look at question 27. Okay, so in question 27, let me bring it up and we'll read it. So 27 says, it's the region in the first quadrant. Okay, so the first thing I'm thinking about, I've got my first quadrant here, bounded by the graph y equals radical x and x equals 4, and I've got the delta area function as a function of y. Look, that's a big clue. Equals y to the 3/2 plus 2. Okay, so this already tells me, right? This says y equals radical x, x equals 4, but everything I do, because my area function is in terms of y, I need to convert these functions to be in terms of y as well, okay? Because I can't convert this. So there's no way I can figure out what that's going to be in terms of x, but I can convert these. Okay, so the first thing I'm going to do when I do this, I want to basically be able to graph this out. So this is x equals 4. So this is my x-axis. 1, 2, 3, 4. So this is my first line right here. So this is x equals 4. Okay, y equals radical x. There's 2. So when x equals 0, y equals 0. I'm going to do this when x equals 4, y equals 2, and it's kind of a curvy line like that. Y equals radical x. So this is the region here that we're looking at. Okay, and we want to be able to find out what's the mass of this region here. Okay, but because I was given this in terms of y, when I go to integrate this, I need to be thinking about things in terms of slivers of dy, which means I need to be going, right? So instead of, if I were doing this as a function of x, I would integrate from 0 to 4. But because I'm going to integrate this as a function of y, I'm actually going to be going from 0 to 2 as a function of y. So this is going to be 0 to 2. My delta area is function of y. I'm going to go area as a function of y dy. So I need to do something about that. So the first thing we're going to do is I'm going to say y equals radical x. I need to square both sides, so y squared equals x. Okay. So if I'm looking at, right, I've got x equals y squared and x equals 4. So if I kind of turn my graph and I'm looking at it like this, right? See if you guys can see that. Okay. So if I turn my graph, I'm going to be integrating things from 0 to 2, right? My upper, you can kind of think about my upper function is x equals 4, and my lower function is x equals y squared. So I need to think about the area of this region here is 4 minus y squared. That's going to give me the area of that region. So I'm going to say upper. So I'll put these in quotes because we're used to thinking things in terms of upper and lower, but we're going this way, right? So my upper, right, is going to equal to 4 minus, right, my new function here in terms of y squared, and that's going to give me the area of this region here. Okay, so now got some of our basic math out of the way. So I'm going to say my mass, right, and remember we're now doing things in terms of y, so I'm going to go from 0 to 2. My delta area function, okay, they gave us that before. Y to the 3/2 plus 2. And then our area, this is going to be 4 minus y squared. And this is dy. Okay. So now again, I need to FOIL these out, right? And then, be able to combine terms. So just as a note, when I go to combine, we're going to need to multiply y to the 3/2 times y squared. Okay. Now remember, this is y to the 3/2 plus 2 because we have the same base, right? Which is going to give us y to the 7/2. Okay, when I actually go to do that. Okay, so just keep that in mind. When I pull out y to the 7/2, you know that it comes from multiplying these two together here. Okay, so I'm going to go from 0 to 2. When I multiply that out, I'm going to get 4 to the 3/2 plus 8 minus y to the 7/2 minus 2y squared dy, right? So first, outer, inner, last gives us these terms. This is a 7, in case you can't read my writing. Okay, now I'm just going to use the power rule when I go to integrate. Okay, so when I go to use the power rule, then I'm going to get 4 y to the 5/2 all over 5/2 plus 8 times y minus y to the 9/2 all over 9/2 minus 2/3 y cubed, and I'm going to go from 0 to 2. Okay, so I basically plug in, all of this stuff here. So I'm going to get 4, 2 to the 5/2 plus 8 times 2 minus 2 to the 9/2 divided by 9/2 minus 2/3 2 cubed. And I'm just going to say subtract 0 because everywhere if I plug in a 0, I've got a y. It'll just come out as 0. Okay. So once I plug it all in, make sure you're really careful about your order of operations on your calculator when you do 2 to the 5 divided by 2, multiplied by 4, then divided by 5 divided by 2. Be very careful, put parentheses around all of these when you go to work it through. The mass that I get, it's 14.69. Okay. So this one had a trick, right? Because the trick that we had to do, let's see if I can put this down into the light so you can see. The trick that we had to do basically was, I don't know if that helps. I kind of forgot this home office thing here. So the trick that we had to do, okay, was to convert our axis, right? So we were originally thinking, I'm going to integrate from x equals 0 to x equals 4. But because our area function was in terms of y, I needed to convert. I can't convert this. So I need to convert my functions, right? So I'm going to integrate as a function of y. That means I got to look at my y-axis. So I'm going from y equals 0 to y equals 2. That just happened to be right where these, functions where they're bounded, where this area is bounded by. Okay, my upper, quote, upper minus lower, right? If I turn it this way, okay, is this minus this. Okay, and as I go from here to here, okay. So I plug those in. That gives me my area of the shaded region times the density, okay, of that shaded region, and the mass, right, is the density times the area, and I integrate it across that region that I'm looking at, and that's going to give me 14.69. And that was question 27. And so that brings us basically to the end of chapter 3.7 for homework problems. I'm happy to answer any other questions. Otherwise, we can move on to another homework, although I kind of want to stop for 3.7, stop this recording for 3.7, and then before I move on to others. if you guys don't have any questions, that's totally fine. Then I'll just wait.